Einstein's special theory of relativity: deep, beautiful, and magical. Today's video is proof via experiment done at MIT of the fact that time travel into the future is possible. Then there will be future videos over the coming weeks. My sources, a lot of sources. I've been studying relativity for 20 plus years, and I have, 15, 25 books on the subject. Here are a few of my favorite books on the subject. I actually studied relativity with Wolfgang Rindler at UT Dallas, and here's his very fine book. Let's start with time travel. You decide to take a trip on a rocket around the solar system for 1 year. You accelerate and eventually reach a really high velocity, say 0.99 the speed of light. When you return 1 year later, everybody else will be 22.4 years older, and you will be only 1 year older. Is this possible? This might seem like science fiction or magic, but I will prove that it is correct via a famous experiment and via mathematical reasoning. There's actually an equation which relates the time of the person on the rocket to the elapsed time of the person at rest relative to that rocket. And it's this equation here. This equation was derived to fit experimental data, but was given meaning by Albert Einstein. For this example, this time is the time traveled by the person on the rocket, which accelerated to the 0.999 the speed of light, and traveled around the solar system for that period of time. This is the velocity, the relative velocity between the person on the rocket which accelerated and the person back at home on Earth at rest. This is the relative velocity, 0.999 c, where c is the speed of light. Okay, so we're going to distribute the squared here, so that gives you 0.999 squared, c squared, cancels this c squared. Plug the rest of it into your calculator, and you get 22.4 years. But just because there's a mathematical equation for it doesn't mean that it's true. So let's take a look at the famous experiment, the Meson decay experiment, which proves through physical evidence that this idea of time travel is actually something we observe in our universe. The entire video, which is about 35 minutes long, can be viewed on YouTube, and here's the link. I will provide an analysis and excerpts from that video. So a mu meson is an elementary particle that comes to us from outer space in the form of cosmic rays. A proton, neutron, and electron, among others, are elementary particles. But those are stable particles. A mu meson is not stable. Mu mesons have a very short life with a half-life of 2 microseconds. A mu meson decays or dies, and when it decays, it forms a neutrino, an antineutrino, and a positron, which is a positively charged electron. If you do not want to view the details of the experiment, here's a summary. Scientists measured the lifetimes of 568 mu meson particles at rest. They then measured the lifetimes of another sample of mu meson traveling near the speed of light, 0.995 the speed of light. They found that those moving at 0.995 the speed of light lived 10 times longer. Let's take one of the mu mesons that lived 0.7 times 10 to the minus 6 seconds while at rest. It still lived for only 0.7 times 10 to the minus 6 seconds in its frame when it was moving at 0.995 the speed of light, but the scientists at rest measured it to be 10 times longer, 7 times 10 to the minus 6 seconds. This proves Einstein's time travel equation precisely. Plug in 0.7 times 10 to the minus 6 seconds here for delta t 0 for the object traveling at 0.995 the speed of light. Here's the velocity, 0.995 c times the speed of light, which is c. The c's cancel, and this turns out to be 7 times 10 to the minus 6, or 7 microseconds. So 7 microseconds is 10 times greater than 0.7 microseconds. So this is proof that time travel is real via an experiment. So proceed if you want more details of the experiment. Otherwise, go to my next video on special relativity to get a mathematical derivation of this equation. The experiment. 2 scientists go to the top of Mount Washington, located in New Hampshire, and they trap mu mesons in a container. The mu mesons they trap are traveling at a speed of 0.995 the speed of light or greater. They know this because they put 2.5 feet of iron above the container. And they know through calculations that only mu mesons traveling at 0.995 speed of light or greater will be able to pass through this 2.5 feet of iron. The mu mesons traveling at such speeds arrive at the container and come to rest. They then measure the time between when the mu meson came to rest in the container and when it decayed or died. They collect mu mesons for 1 hour, and after such 1 hour, they collect 568 mu mesons. For the 568 mu mesons, the scientists have collected and tabulated the lives for each one. Here's a part of the video that summarizes their collection of the data of the mu meson decay times at the top of Mount Washington. If some of this is confusing to you, hang in there. I'll come back and explain to you in more detail what they're talking about.
So here's our finished chart, based on the 568 counts which we got during this hour.
The 568 counts we have plotted on our chart are the result of 1 hour's run. Previously, we had taken 5 different runs, each for an hour, and their average comes out 564, so that the 568 we have plotted are indeed a good sample of the number of mesons decaying in our scintillator every hour.
So you can think of the mu mesons as coming down in a steady rain from hour to hour. Many mesons live for as long as 1 microsecond. Fewer live for 2 microseconds. By the time we get to 5 microseconds, only a small fraction of the original number remain. And by the time we get down to 8.5 microseconds, which is the longest time we can see on the scope face, only a very few mesons are decaying.
That chart is a pictorial representation of the decay times of those mesons which had stopped in the scintillator before we began to measure their decay times. They were at rest with respect to us during the time shown on the chart. Now we come to the heart of the experiment. What happens to the decay times of these mu mesons when, instead of being at rest with respect to us, they're shooting on down by us with speeds nearly that of light? Let's look at the chart in more detail.
For instance, here's a meson which lived for 3.5 microseconds sitting in our scintillator. Suppose we hadn't stopped it. Where would it have gone? Here we are, up on top of Mount Washington, 6,300 feet above sea level. We stopped that meson up here. If we hadn't, it would have gone on for 3.5 microseconds down below before decaying. Now how far would that have been? It would have gone a distance 3.5 times 10 to the minus 6 seconds times its speed v. So in order to know just how far it would have gone before decaying, we need to know its speed v.
Fortunately, we do know the speed of the mesons which stop in our scintillator because we know how far a charged particle of a given mass and speed can go through matter. A mu meson entering the top of the iron with 0.9950 times the speed of light gets just into the top of the scintillator before it stops. With any less than 0.9950 C, it stops in the iron. With slightly greater, 0.9954 C, it goes down and stops in the bottom of the scintillator. With greater speed than that, it goes on through and into the mountain. So the mesons we count have speeds between 0.9950 and 0.9954 the speed of light. For our present purposes, we don't need that accuracy. Let's just say that they have approximately the speed of light and go close to 1,000 feet per microsecond.
That is, v is 1,000 feet per microsecond, or this particular meson would have gone on 3,500 feet before decaying. Now this one, which lasted only 2.4 microseconds, would have gone on only 2,400 feet before decaying. This one, which lasted nearly 5 microseconds, would have gone on nearly 5,000 feet. I might, in fact, simply relabel this axis over here in thousands of feet. And then we can simply ask, how many of our mesons would live to reach sea level, which is 6,300 feet down? Let me put a string across here at 6,300 feet and simply count how many of our mesons would have gone down that far and reached this level. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 4, 25, 26, 27. So, if we take our equipment down to sea level, we expect to find 27, or about 27, mesons stopping and dying in our plastic each hour.
That calculation is based on the assumption that mu mesons decay, that is, keep time, when they are in flight in the same way as they do when they are at rest with respect to us.
So the scientists' estimate of how many mesons would live long enough to travel to the bottom of Mount Washington. So recall the mu mesons they trapped were traveling at 0.995 the speed of light or greater. Since this is so close to the speed of light, the scientists assumed that the mu meson speed was the speed of light, which is 1 times 10 to the 9th feet per second. They used 1,000 feet per microsecond, but that's the same thing as 1 times 10 to the 9th feet per second. So the distance the mu mesons must travel to get from the top of Mount Washington sea level was 6,300 feet. The time it takes to travel 6,300 feet at the speed of light is simply time is equal to distance over speed. Okay, that's a simple formula we use all the time. So 6,300 feet is the distance. The speed of the mu meson is 1 times 10 to the 9th feet per second. That ratio gives you 6.3 times 10 to the minus 6 seconds. That's 6.3 microseconds. So therefore, the scientists conclude correctly that only mu mesons that live this long or longer would make it to the bottom of Mount Washington, located at sea level. And based on their experiment, only 27 mu mesons survived this long or longer to be able to travel that distance. Here's what the scientists did at the bottom of Mount Washington. To ensure that the collection at the bottom was similar to the collection at the top, they used 1.5 feet of iron instead of the 2.5 feet of iron at the top. 1.5 feet of iron plus 6,300 feet of air will have the same slowing power as 2.5 feet of iron. So now the collection at the bottom is similar to the collection at the top. Only mu mesons with a velocity of 0.995 the speed of light or faster will be able to pass into the collector. So will the life of the mu meson in microseconds as measured by the scientists at rest change due to the fact that the mu meson was traveling near the speed of light over the path of the 6,300 feet descent? The scientists counted the number of mu mesons at the bottom. They counted 412 for the hour. This far exceeded the number that they expected. So let's go to that part of the video where they discuss their actual count.
So we're over here at Cambridge, Massachusetts, 150 miles away, and we're counting the survivors of the mesons incident at the 6,000 foot level above us here. The average intensity of cosmic rays is the same over horizontal distances of many hundred miles across the Earth. So there are approximately 568 mesons coming down 6,000 feet above us during this hour. Now there's one thing different about our equipment down here.
On top of Mount Washington, we used a layer of iron about 2.5 feet thick to select our mesons. But between here and 6,000 feet, there's a layer of air equivalent in slowing down power to 1 foot of iron. So to compensate, we've removed 1 foot of iron from our stack. We've removed that iron in order that the mesons, which stop in our scintillator here, have a speed 0.995 c when they pass the 6,000 foot level above us. That's the same speed which the mesons had when they entered the iron on top of Mount Washington and stopped in our scintillator. Now this is only one of many effects we've had to take into account in this experiment. For instance, not all mu mesons come straight down. Also, a few mu mesons are produced by other cosmic rays between 6,000 feet and sea level. In addition, some mu mesons which stop in our scintillator make nuclear interactions. We believe that we've properly taken all these effects into account and that their effect on our final result is small. Now, let's take a look and see how the counts are coming in.
13. That's a lot more than we expected. Let's go on and take the full hour's count and get some good statistics. 409. 410. 411. 412. Okay, that's the hour. Instead of 27, we have 412 mesons left at sea level. That's way up here on our chart. I've been tabulating here the number of mesons surviving as a function of time on our meson decay distribution clock. And 412 corresponds to only about 0.7 microseconds.
So the scientists counted 412 per hour. They expected to get 27, which are the mu mesons which live for 6.3 microseconds or more, which is the time required to make it down the mountain of 6,300 feet before dying or decaying. So how is this explained? The difference between the mu meson lifespans at the top of Mount Washington and the bottom was that at the top, the mu mesons were at rest in the container. And per the time dilation equation, for velocity is equal to 0, okay, the mu mesons were not traveling relative to the scientists at rest. They were both at rest. We put V 0 here. This comes out to 1. So the lifetime of the mu meson is measured by the scientists was the same as the actual lifetime of the mu meson measured in its frame. But over the distance of 6,300 feet, the mu mesons were traveling at 0.995 the speed of light. So how long would the scientists measure a lifespan of a mu meson to be? Now the scientists are at rest, but the mu meson speed here is 0.995 c. So to count 412 per hour, mu mesons with a lifespan of 0.7 microseconds when they were at rest relative to the scientists must now have lived longer due to their now high velocity relative to the scientists. Let's see if Einstein's time dilation equation explains the lifespan difference of the mu meson. So this time is the time of the object moving, and the object moving here is the mu meson. So I'm going to plug in 0.7 times 10 to the minus 6 seconds for this value right here. Its velocity relative to the stationary observer is 0.995 c. Plug that in for v here. C squared cancels this c squared. Plug this into your calculator and you get 7 microseconds. So 7 microseconds, not 0.7 microseconds, is the time measured for the life of a mu meson traveling near the speed of light as measured by the scientists. 0.7 microseconds is sufficient time for this mu meson and all others living longer than this to make it to the bottom of Mount Washington. 7 microseconds times 1,000 feet per second is 7,000 feet, which is greater than 6,300 feet. So 412 mu mesons lived longer than 0.7 microseconds, and that explains their count. Realize, of course, that the mu meson still only lives for 0.7 microseconds in its own frame.